Okay, free body diagrams. I'm going to do this really quick. Ready? You have here a fighter jet. Okay. The fighter jet has forces acting on it. What forces do you think are acting on this fighter jet?
Gravity.
Gravity down.
Is there a force forward?
No, thrusters on the back. Pushing. Like that.
There is a force. No, there is a force.
So the thrusters are pushing
There's thrusters on.
backwards, let's say, but that's pushing the jet forwards, right?
Yes.
So the forces on the jet, the force forward, if I'm pushing the throttle, the force forward is called thrust.
Thrust.
Oh.
Yeah.
I believe there's also thrusters underneath that thing as well.
There might
If that's an aircraft carrier. If that's an aircraft carrier.
So thrust forwards. Now, notice the jet is pushing. Oh, it's flying this way. Sorry, I should do this. Left thrust. The jet's flying to your left. Okay. Hey, this is important. Listen. Sorry, I know I'm stretching you out a little bit today. When the jet's being pushed forwards, it doesn't matter that the engine is pushing rocket fuel out that way. The jet itself is being pushed to the left. And so we draw the arrow. This is a free body diagram. You're going to learn how to do these right now. This is the object. So we just draw a box, but it's a jet. Because we don't want to draw jets every time, right? So we just draw a box. And we put the arrow out. This is the thrust force because it's pushing the jet to the left. We don't care about anything else. We just care about the forces acting on the jet and which way it's being accelerated. Is there a backward force acting on the jet as well?
Yeah.
Yes.
Good. This,
Air.
I would call this force of friction. You could also say
Air resistance.
air resistance.
We're on the same wavelength, buddy.
Very good, Sam and Matthew and Declan and whoever said that. Is there an upward force on the jet?
Yeah,
Yes.
lift of the wings.
Sam?
Lift of the wings.
Oh, he's on it today. I'm going to give it to him. This one is there a word that you always want to cursive write and not print?
Yeah.
That lift is that word for me. I can't print it. I have to write it. I'm gonna give a caveat here. This jet actually has very little lift. It flies like a potato chip. It doesn't really have.
Doesn't need it when it hits the thrust.
It doesn't need it. You just push the thing and the jet goes right. It's so powerful. But a normal plane, like a plane you would ride in going to Europe or something, the wing provides a lot of lift force to keep that mass up in the air. Okay, so there is an upward force. And what's the other force?
Gravity.
Good. Gravity pushing down. Now, let's say that this jet is flying at, let's say, 200 meters per second. What can you say about those four forces?
They are the net force.
They're,
Okay.
they're cool. They're, what's
Good.
that name?
He's really doing well today, isn't he? So, as you said, net force. Sam said they're all equal. So, Peria, if the forces are all equal, what is the net force? Very good. Very good. If this jet is flying at a constant velocity, does not have to be zero. If it's flying at a constant velocity, all these forces are equal, and the net force is 0. If it's accelerating forward, then what would you say?
It's unequal.
It's unequal, this is no longer 0, and which is the biggest force?
Forward.
This is going to be bigger, right? What if it's slowing down?
Air resistance.
Then this is smaller and air resistance is bigger, right? What if it's falling?
Gravity's bigger. Lift is
Yeah.
down.
Is gravity going to grow
No.
No, gravity stays the same. But this will shrink, right? And then the jet will go down. So these forces they all add up to a net force. Moving on. So a free body diagram shows the magnitude and direction of all the forces acting on an object. So we put them all in there. Generally, we just draw a box. We don't draw doggies and things, although that's kind of fun too. We draw the force arrows coming out from the center, not in towards the object. So if you're pushing something, even though you're pushing the box, you would draw the arrow from the box out, because the box is being accelerated that way. Does that make sense? Matthew?
For like your net force, would you do normal force up and gravity down?
Exactly, exactly. So I'm going to show that in a second here. Remember the size of the arrow? You don't have to get into specifics, but if the thing is, let's say it's falling downwards, the gravity arrow would be bigger. Okay? So, try this. You have a box sliding along a floor at a constant velocity. Draw a free body diagram where, first, the floor is frictionless, so no friction. And then the floor does exert a force of friction. Try all the arrows. See what you come up with. It's on a floor, right? So imagine these sitting on a floor. We don't draw the floor in the free body diagram, but how's my phone? Is it still working? For now, my storage is not full. Okay, let's do this together. What's the first force you think of?
Gravity.
Gravity. It's definitely going to be gravity. So we draw F with a little g, force of gravity down. What else is happening here?
Normal force.
Very good, excellent. So the box is not falling, it's being supported by the floor. So there is a normal force. What would you say about these two?
Equal.
They cancel
Good,
each other
they're equal. In this situation, is there any other force?
out. The force of the force of the box sliding along.
What's the two most important words in this sentence?
A constant velocity.
Constant velocity. That means acceleration is what?
0.
Which means F net is?
0.
If there is no friction acting on this box, then can there be a forward force pushing it forward? No. So if there is no friction here, there's no other forces on this box.
But wouldn't there have to be an initial force to push it?
Initially, something pushed it,
Oh, okay.
like something pushed the Earth around the sun initially. But right now, there's no force pushing us forward.
Okay.
Okay? This doesn't really exist in the real world, right? It's only like in theoretical physics land. There's no surface with no friction. You kind of have to go to space. We have really low friction. Okay, what about here? Is there still gravity?
Yes.
Yeah. Still normal force?
Yes.
Are they still equal?
Yes.
Yes. Here, we have a friction force. Which way do you want to push it?
That was
You want to push it this way?
Yeah.
Okay, so if you're pushing it to the right, which way do I draw the arrow
for what?
for the applied force?
To the right.
Good. So you're going to push it this way, and I'm going to make it different, different length. And I would say FA, this means F applied. So we're applying a force forwards, but it's moving at a constant velocity, so can I be finished here? No. What else do I need to add? Good.
Small arrow.
And would I do a small arrow or same size or bigger?
Small.
So small. Whoa.
Small.
Same size.
gotta be the same, right? It's gotta be the same. If you're moving at constant velocity, you can't have any net force here, so no arrow can be bigger. Well, they can be, these two can be bigger than these two, but these two have to be the same, and the vertical two have to be the same, so that the sums are 0. So this is gonna be force of friction. Okay?
That seems so counterintuitive.
Yeah, it does seem counterintuitive at first, for sure, I agree.
It seems like the force applied should be more than the friction because you're moving in that
Yes.
direction.
Yes, and I'm really glad you're thinking about that. And I hope the rest of you are as well, and try to get that concept straight in your mind. That if it's constant velocity, there can be no forces winning.
But if
All the
it's-
forces are tied. The moving part doesn't matter. If you're moving, like if you're driving the car down the highway at 90, your engine's pushing you forward, and friction is pulling you back, and those two forces are the same.
Then how are you still moving forwards though?
You tell me, how are you still moving forwards? Who can help with this? Think about it this way. Car's sitting still. There's no force forward, there's no friction. We're even, right? Net force is 0. As soon as I apply a force, what happens?
There's a one opposite reaction.
If I apply a force, there's going to be a net force. So I hit the gas pedal, and my applied force starts to build. And what's going to happen to the car?
It's gonna move forward.
Yeah. It's going to accelerate, right? As I accelerate, I get faster and faster, yes?
Yes.
What happens, what force grows as I get faster?
The force of friction.
The force against
Right.
it.
So I start off, have force accelerating, but as I get faster, this force grows. And eventually they're the same. If that wasn't the case, I would keep getting faster, right? If this force is bigger than this force, I'm accelerating. I'm not just going constant velocity, I'm increasing my velocity. As I increase my velocity, the friction gets bigger. Now I'm even, but I'm driving at 90. I'm not sitting still. Then I'm driving along, and then I let the gas off. And what happens now?
Now the-
Friction will come in.
Now you're decelerating.
Right, exactly. Now I'm accelerating in this direction. Still moving forward, but I'm slowing down, right? And what happens to this as I slow down?
It becomes less.
Friction gets less and less and less until these two are equal again. Now I'm going at a slower speed. Does that make sense?
Wait, so there could be a box diagram and you could be going 90 or you could be going 1 kilometer and that's the same thing.
Absolutely right.
So,
At 1 kilometer an hour, this is very small and this is very small. At 90, this is bigger and this is bigger. But in both cases, they're equal.
I see.
Good thinking, good thoughts. I'm going to give you a little sheet with a bunch of situations of free body diagrams, and I want you to draw them all. Yay, we made the video.